carbon dating and more. Can you tell me about carbon dating? Carbon dating, also known as radiocarbon dating, is a method used to determine the age of organic materials based on the decay rate of the radioactive isotope carbon-14, 14C. Carbon-14 is formed in the upper atmosphere by the interaction of cosmic rays with nitrogen atoms, and it is taken up by living organisms through respiration and food consumption. When an organism dies, it stops taking in carbon-14, and the carbon-14 in its body begins to decay at a known rate. The half-life of carbon-14 is 5,700 years, which means that after this time, half of the original amount of carbon-14 in a sample will have decayed into the stable isotope nitrogen-14, 14N. By measuring the amount of carbon-14 remaining in a sample, scientists can determine how long ago the organism died. Carbon dating is particularly useful for dating organic materials that are up to about 50,000 years old, such as wood, bones, and charcoal. It is not as accurate for materials that are millions of years old, such as rocks and fossils, because the amount of carbon-14 remaining in the sample is too small to be measured accurately. Carbon dating has revolutionized the fields of archaeology and anthropology, allowing scientists to accurately date artifacts and human remains, and to better understand the history of human civilization. Show me the equation to find the age of a piece of bone about 20,000 years old. The equation for calculating the age, T, of a sample using radiocarbon dating is T equals lane NF/no minus 0.693 x T1/2, where 1. NF is the amount of carbon-14 remaining in the sample, measured in atoms or moles. 2. No is the initial amount of carbon-14 in the sample, assumed to be the same as the amount in living organisms at the time the sample was taken. 3. T1/2 is the half-life of carbon-14, 5,700 years. To find the age of a piece of bone that is approximately 20,000 years old, we would first need to determine the amount of carbon-14 remaining in the sample, and compare it to the amount of carbon-14 that would have been present in the bone when it was alive. Assuming that the bone contained the same amount of carbon-14 as living organisms at the time it died, we can estimate that the initial amount of carbon-14 in the bone was about 1.3 by 10 to the power of 13 atoms per gram of carbon, or 13,000 atoms per milligram of carbon. If we assume that the amount of carbon-14 remaining in the bone is 1/8 of the initial amount, based on the fact that 3 half-lives have elapsed since the bone died, then we can calculate the age of the bone as follows. T equals lane NF/no minus 0.693 x T1/2 T equals lane 1/8 x 1.3 by 10 to the power of 13, 1.3 by 10 to the power of 13. Minus 0.693 x 5,700 T equals lane 1/8, minus 0.693 x 5,700 T equals 20,000 years. Therefore, the bone is estimated to be approximately 20,000 years old. It's important to note that this is just an estimate, and that carbon dating is subject to some sources of error, such as contamination and variations in the carbon-14 to carbon-12 ratio in the atmosphere over time. Okay, do another, but this time it's plant about 40,000 years old. Sure, to calculate the age of a plant that is approximately 40,000 years old using radiocarbon dating, we can use the same equation as before. T equals lane NF/no minus 0.693 x T1/2. Assuming that the plant contained the same amount of carbon-14 as living organisms at the time it died, we can estimate that the initial amount of carbon-14 in the plant was about 2.6 by 10 to the power of 13 atoms per gram of carbon, or 26,000 atoms per milligram of carbon. If we assume that the amount of carbon-14 remaining in the plant is 1/16 of the initial amount, based on the fact that 4 half-lives have elapsed since the plant died, then we can calculate the age of the plant as follows. T equals lane NF/no minus 0.693 x T1/2 T equals lane 1/16 x 2.6 by 10 to the power of 13, 2.6 by 10 to the power of 13, minus 0.693 x 5700 T equals lane 1/16 minus 0.693 x 5700 T equals 40,000 years. Therefore, the plant is estimated to be approximately 40,000 years old. Again, it's important to note that this is just an estimate, and that carbon dating is subject to some sources of error. What else do I need to know? Here are a few additional things to keep in mind when thinking about carbon dating. Carbon dating is based on the assumption that the ratio of carbon-14 to carbon-12 in the atmosphere has remained constant over time. However, this ratio can vary depending on factors such as solar activity and volcanic eruptions. Scientists use tree rings, ice cores, and other methods to calibrate and verify carbon dating results. Carbon dating is only accurate for materials that are less than about 50,000 years old. After this point, the amount of carbon-14 remaining in a sample is too small to be accurately measured. Other dating methods, such as uranium lead dating or potassium-argon dating, must be used to determine the ages of older materials. Carbon dating can be affected by contamination from sources of modern carbon, such as groundwater, soil, or human activity. To minimize this risk, scientists take great care in collecting and preparing samples, and they use a variety of methods to check for contamination. Carbon dating is just one tool that scientists use to understand the age of objects and materials. It is often used in combination with other dating methods, as well as with other types of scientific analysis, to build a more complete picture of the past. Tell me more about other dating methods, such as uranium lead dating or potassium-argon dating, must be used to determine the ages of older materials. And the equations solving for a 7,500-year-old bone. Uranium lead dating and potassium-argon dating are two other methods that scientists use to determine the ages of rocks and minerals that are too old for carbon dating. Here's a brief overview of each method. Uranium lead dating. Uranium is a radioactive element that decays into lead over time. By measuring the ratio of uranium to lead in a rock or mineral, scientists can calculate its age. This method is particularly useful for dating rocks that are billions of years old. Potassium-argon dating. Potassium is a common element found in rocks and minerals, and it decays into argon over time. By measuring the ratio of potassium to argon in a rock or mineral, scientists can calculate its age. This method is particularly useful for dating rocks that are millions of years old. To solve for the age of a bone that is approximately 75,000 years old using uranium lead dating or potassium-argon dating, we would need to know the initial amounts of the radioactive elements and the daughter products, lead or argon, in the bone, as well as the rates at which those elements decay. The equations for uranium lead dating and potassium-argon dating are fairly complex and involve multiple steps. Here's a simplified version of the equation for uranium lead dating. T equals 1/lambda, x lane d plus p/n. Where 1. T is the age of the sample. 2. Lambda is the decay constant for uranium-238, the rate at which it decays. 3. D is the amount of lead-206 in the sample. 4. P is the amount of lead-207 in the sample. 5. N is the amount of uranium-238 in the sample. To solve for the age of a 75,000-year-old bone using uranium lead dating, we would need to know the amounts of lead-206, lead-207, and uranium-238 in the bone, as well as the decay constant for uranium-238. Similarly, to solve for the age using potassium-argon dating, we would need to know the amounts of potassium and argon in the bone, as well as the decay constant for potassium-40. It's worth noting that both uranium lead dating and potassium-argon dating have their own sources of error and uncertainty, and they are often used in combination with other dating methods and lines of evidence to build a more complete understanding of the past. Do you know the decay rates? Yes, the decay rates for uranium-238 and potassium-40, which are used in uranium lead dating and potassium-argon dating, respectively, are well established. The decay rate for uranium-238 is approximately 4.47 by 10⁻10 per year, which means that half of the uranium-238 in a sample will decay into lead-206 in approximately 4.5 billion years. The decay rate for potassium-40 is approximately 1.25 by 10⁻10 per year, which means that half of the potassium-40 in a sample will decay into argon-40 in approximately 1.3 billion years. These decay rates are used in the equations for uranium lead dating and potassium-argon dating to calculate the ages of rocks and minerals. However, it's important to note that the decay rates can be affected by external factors such as temperature and pressure, so scientists take care to measure them accurately and to account for any potential sources of error. Could you put that in a balanced chemical equation for me? Sure, here are the balanced chemical equations for the decay of uranium-238 and potassium-40. Uranium-238 decay. U-238Th234 plus alpha, alpha particle, or 238_92 U-234_90th plus 4_2 alpha. In this equation, an alpha particle, which is a helium nucleus, consisting of 2 protons and 2 neutrons, is emitted as uranium-238 decays into thorium-234. Potassium-40 decay. K40R40 plus beta, beta particle, or 40_19 K40_18 R plus 0_1 beta. In this equation, a beta particle, which is an electron, is emitted as potassium-40 decays into argon-40. Okay, start at the basics on that please. Certainly. At its most basic level, radioactive decay is a process by which the nucleus of an atom loses energy and transforms into a different type of atom. This transformation can occur in several ways, but the most common types of decay are alpha decay, beta decay, and gamma decay. In alpha decay, the nucleus of an atom emits an alpha particle, which is a cluster of 2 protons and 2 neutrons. This causes the original nucleus to lose 2 protons and 2 neutrons, which means it transforms into a different element. For example, when uranium-238 undergoes alpha decay, it transforms into thorium-234. In beta decay, the nucleus of an atom emits a beta particle, which is an electron or a positron, a positively charged electron. This causes the number of protons in the nucleus to change, which means the atom transforms into a different element. For example, when potassium-40 undergoes beta decay, it transforms into argon-40. Finally, in gamma decay, the nucleus of an atom emits a gamma ray, which is a type of high-energy electromagnetic radiation. Gamma decay does not cause the atom to transform into a different element, but it can result in the release of energy and a change in the stability of the nucleus. These different types of decay are characterized by specific decay rates, or half-lives, which indicate how long it takes for half of the atoms in a sample to undergo decay. Scientists use these decay rates to determine the ages of rocks, fossils, and other materials through a process called radiometric dating. Go on. Radiometric dating is a method of determining the age of a sample by measuring the amount of radioactive isotopes it contains and comparing it to the amount of stable isotopes in the sample. This is possible because the rate at which radioactive isotopes decay is constant over time. For example, if a rock contains a certain amount of uranium-238 and a certain amount of lead-206, which is the stable isotope that uranium-238 decays into, scientists can calculate how long it has been since the rock formed based on the ratio of uranium-238 to lead-206. By knowing the half-life of uranium-238 and the current ratio of uranium-238 to lead-206, they can determine how much time has passed since the rock was formed. Other types of radiometric dating include potassium-argon dating, which is used to date volcanic rocks and minerals, and carbon-14 dating, which is used to date organic materials that are less than 50,000 years old. Each type of radiometric dating has its own unique strengths and limitations, but together they provide a powerful tool for understanding the history of the Earth and the life that has inhabited it. Thanks for watching. Subscribe and like.